Swayam Prabha. Digital India. Educated India.
Hello everyone, we are continuing our discussion on combustion of metals, and in the previous lecture I think we had started discussing about the metal combustion regimes. Now as we told ourselves that before considering the various metal particle combustion regimes, particularly like diffusion control or kinetic control, we had told ourselves that we want to take the analogy of droplet burning features of normal liquid fuel, and we just compare the similarity of the droplet evaporation or burning to the metal particle combustion, in a sense that we compare the burning of single metal particle with that of the droplet of the droplet combustion of single liquid droplet. Now we had talked about the surface regression of the evaporating droplet, and there we have talked about the mass flask with respect to the mass regression rate, and we wrote some equation there. So, let me just repeat some of the things there, and we want to use the basic equations derived from the droplet combustion features, and we want to use the similar equations for the burning of single metal particle. So, let us go ahead with what we have done in the previous lecture. I will just repeat some of the things and we will just move ahead to learn what are the required for the metal particle combustion. So, as I said, we take the similarity to evaporation and combustion of single droplet. So, in order to do that, we already consider a single droplet in a quiescent environment, as we said. So, the outside is oxidizing media is there, which is like oxidizer. This is fuel droplet, and the droplet is producing fuel vapor. There will be like flame front, which is going to provide the heat to the droplet for evaporation of the droplet. So, droplet will keep on regressing. So, the fuel vapor leaves the surface of the droplet. We said that the rate at which the fuel vapor leaves the surface is m dot f, and if we want to write that in terms of mass flask at the surface, so this was we said is the rate at which fuel vapor leaves the surface, and corresponding mass flask was denoted as m dot f double prime. So, this was defined as the mass flask at the surface. So, we can relate this rate at which fuel vapors leaves the surface. So, mass regression rate at the surface, we can relate that to mass flask by the equation m dot f equal to 4 pi r square into m dot f double prime, where r is the radius of the droplet. Now, what it is happening here, that the diffusion of the fuel vapor is actually taking place in the medium of fuel vapor and oxidizer vapor. So, there will be the oxidizer vapor here and the fuel vapor is also here. So, there is a media of mixture of fuel vapor and oxidizing vapor, and we consider the density comprising the fuel vapor and oxidizing vapor as the rho. There is a concentration, the diffusion will take place due to the bulk flow and the concentration gradient of the fuel vapor. Now, we had denoted the mass fraction of fuel vapor of fuel vapor by YF, and we define YF as the mass of fuel vapor divided by the mass of fuel vapor plus mass of oxidizer vapor. You see, this media is consisting of both the fuel vapor and the oxidizer vapor. So, we are considering the mass fraction as m dot F by m dot F plus m dot O, mF divided by mF plus mo. Now, if we now write the mass flux equation of the fuel vapor, what we can write? We can write that this is going to be equal to YF into m dot F double prime plus m dot O double prime minus rho d dyf dr. So, dyf dr is basically going to give us the concentration gradient. So, dyf dr is happening due to the concentration, this is the concentration gradient. So, we must need to consider the mass flux due to the fuel vapor due to the concentration gradient, we need to incorporate in this equation. So, the term this one is gives the mass flux of fuel vapor due to the concentration gradient dyf dr. So, we are considering the concentration gradient in the radial direction, because this is happening in the radial direction. So, this is like radial direction. Okay. Now, we have considered d is as the diffusion coefficient or the mass diffusivity, we have already defined that. So, if we just look at carefully, only the fuel vapor is actually moving out into the ambience. If you look at carefully, the fuel vapor is actually going out in the ambience of oxygen. So, we can consider that the m dot O double prime supposed to be like 0. So, what you can get from this equation, if we just if you rewrite this one in terms of like the m dot F double prime, which is m dot F by 4 pi r square, if you just simplify this and write this in terms of m dot F, we can get minus 4 pi r square rho d by 1 minus YF into dy f dr. I think we have done this one in the previous class, and then we have said we have also simplified it further in terms of like dyf dr, sorry not dyf dr, we had said that we want to do the we want to take this dyf in one side. So, I think we had written minus dyf by 1 minus y by f, that was equal to m dot f by 4 pi rho d into dr by r square. So, we just modify these equations a bit. Now, we also said that if the concentration of fuel vapor at the droplet surface, so which is like at r equal to r s, which is the droplet surface, we can denote the concentration of fuel by y f s, and at r equal to infinity means far field, we can denote the concentration of fuel as f infinity. Now, if you integrate this equation, what we can write? We can write this is going to integrate from y f s to y f infinity minus dy f by 1 minus y f, and this is going to be like surface of the droplet to the infinity m dot f by 4 pi rho d dr by r square. Okay, let us say this is equation B. If you do this integration using the boundary condition, what you can get? We can get ln 1 minus y f infinity by 1 minus y f s is going to be equal to m dot f by 4 pi rho d by r s. R s is the radius of the droplet. Now, from here we can write the mass flow rate of the fuel vapor from the droplet surface. We can write m dot f is going to be equal to 4 pi into rho into d into r s into ln 1 minus y f infinity by 1 minus y f s. Okay. Now, if we look at carefully this term 1 minus f a y f s by 1 minus y f s, sorry 1 minus y f infinity divided by 1 minus y f s is kind of a gives us an indication that this is kind of a transport of fuel vapor, transport of fuel vapor from the surface of the droplet. So, this is we can simplify by denoting one transport number B, and we define it as y f s minus y f infinity by 1 minus y f s, and if we incorporate this transport number into this equation of the rate of generation of fuel vapor, if we write that equation by incorporating this transport number, we can write m dot f is going to be equal to 4 pi rho d r s ln 1 plus b. Okay. This is one of the important equations which we can use later on for understanding the evaporation of the droplet. We can try to find out the evaporation rate constant, and how we can do that we will just show in a minute. So, if you recall what we already defined, that evaporation parameter or evaporation constant, under steady state vaporizing conditions for a particular in a particular ambient condition, for which if we are given the rho d, in fact the density of liquid, transport number, if they are specified, we can say the value of this beta v, which was defined as the evaporation parameter, is kind of coming out to be the constant, and that is why this is also known as evaporation constant. Of course, the value of beta v is going to increase as the temperature of the droplet increases. We can also say that the beta v is going to be related with the that d square law. We can get it from d d 0 square by dt is going to be equal to beta v. So, if we consider this equation, we can actually try to find out the time taken for the evaporation by denoting the time, let us say by T v. So, what you can say, the time taken for evaporation T v, it basically is going to be like when all the droplet all fuel is evaporated. So, basically d 0 is going to be none. So, if you integrate this from d 0 to nil or none, we can actually get the time taken for the evaporation. So, simply we can get T v is going to be equal to d 0 square by beta v. And what about our beta v? We had already looked at in the previous equations. We already defined the beta v there, where we had incorporated the beta v in terms of the 4 into m dot f divided by rho L. If you recall what we had earlier, this was given as 4 into m dot F divided by 4 pi, sorry, 4 mb by rho pi d. This was like liquid. So, if you put this in terms of this equation, you will finally will get, if you replace the values, we can get, instead of radius, if you write in terms of diameter, we can get the value of, sorry, the time taken for evaporation will come something like an equation d0 square into rho L by 8 rho d ln 1 plus b. So, basically we are replacing m dot f from this equation, and we are writing r as in diameter terms, which is d0 square which is d, and if you just simplify the equation, you will get this type of relationship. So, which tells us that the evaporation time taken for the sorry, this is we can, there is a mistake in the equation, sorry, I guess we can check this one. Okay, there is a mistake from this one. You just simplify this by replacing m dot f in this equation, and you will end up getting this rho d is, yeah, you are right. I think it was correct. It was denoting the d0 square by this thing. So, it should be like d0 square into rho L by 8 times rho into the diffusivity into ln 1 plus b. Yeah, this was correct. So, what you can say that the time taken for different droplets is going to vary if the as the droplet diameter decreases, the time taken is going to reduce. Now, if we consider the droplet evaporation at a high pressure, it may take like longer period of time. In many occasions, if we consider the droplet evaporation for typical droplets in a spray, which is of the order of like 100 micron or so, the droplet evaporation time can be the tens of milliseconds. Okay. Now, we can proceed further by taking this analogy that in case of droplet combustion, of course, there is a flame exists there, and flame is going to provide the heat to the evaporation of the droplet and generation of fuel vapor. So, if you just look at it further for the combustion of a droplet, what can we say? Because ultimately the idea behind doing this exercise is to try to understand and use the similar equation for a single particle. So, what we are trying to do here is we try to understand what is going to happen for single metal particle. So, we are trying to use this equation for droplet combustion in the context of single metal particle combustion. So, let us look at, if we just consider this combustion of a droplet. For combustion of a droplet, what you can say? The droplet is there, there will be oxidizer. So, this is our fuel, there will be oxidizer, and of course, the flame zone will be there somewhere over here. This is let us say flame zone. So, flame is going to transfer heat to the droplet for further evaporation. We can say that this is the radius of the droplet, let us say RS. One can actually understand the radius of the flame also, because we are considering the spherical droplet, and from the flame we can say the products are forming. So, the mixing of fuel vapor and oxidized vapor is taking place. So, in the similar way we can extend this our understanding, and we can modify the transport number what we have just done for the evaporation case, we can simply do the transport number for the combustion of a fuel droplet as well. Now, what we can see here, once the combustion is taking place, we can considering that the spherical symmetry is maintained. So, the flame is kind of spherical around the flame around the droplet. From here also we can say the fuel vapor is vaporizing away from the droplet. What we can consider here is that it is maintaining a stoichiometric mixture of fuel vapor and an oxidizer vapor. So, let us say we consider the fuel by oxidizer vapor stoichiometric is maintained there. So, if we consider that, we can modify the transport number and we can write in terms of including this fuel by oxidizer ratio, which is like the mixture ratio stoichiometric. So, the oxidizer vapor can stretches to infinity, where we can say the temperature is T infinity, the surface temperature we can say T s, we can consider the surface temperature T s, the temperature at the infinity or the far field is the T infinity. Now, the product of combustions are going to come out from the flame and they can mixed in this zone. The heat which is required to vaporize the fuel droplet is actually coming from the enthalpy of the ambient and the heat release from the stoichiometric flame zone. So, basically the heat is coming via T infinity minus T s plus some some chemical energy generated due to the combustion. So, if we say that heat release taking place due to the combustion and heat transfer is taking place to the fuel surface for further vaporization. So, that way we can actually modify this transport number, and we can say that for this it is going to be a coupling function between the coupling function based on the coupling function between the energy and the oxidizer species. So, we are writing based on coupling function between the energy and oxidizer species, and we can modify this as fuel by oxidizer ratio stoichiometric into oxidizer mass fraction into there is one heating value or calorific value or heat of reaction of the fuel. So, let us say we denote that heat of reaction of the fuel plus the enthalpy Cp into T infinity into T s, this divided by the latent heat of vaporization. So, let us define this parameter what we just said, where this is B is the mass transfer number. We can define the newer parameter what I just said, fuel by oxidizer is the mixture ratio at the stoichiometric condition or stoichiometric mixture ratio. T infinity is the gas temperature far from the surface, Cp specific heat, this delta H Rf is the heat of reaction of the fuel. Of course, this is given on the basis of per unit mass. T s is the surface temperature, what else? Yeah, this L vaporization is the latent heat of vaporization. So, if we just want to use the same thing, same equation for a particle with heterogeneous surface reaction, for example, like boron particles, what we said that there will be like heterogeneous surface reaction. For example, like carbon particles is going to have like heterogeneous surface reaction. So, what we can say there that due to the heterogeneous surface reactions, we can modify this equation a bit, and also we can say that there is no volatility of the fuel at the surface. So, YFS is going to be equal to so this is basically based on the oxidizer and energy. If we say that, because we have considered this based on coupling function between the energy and oxidizer. So, if we want to use this for the same thing for the fuel based on the coupling function between the fuel and oxidizer species equation, then we can modify it slightly. So, this is, remember, this is based on the coupling function between the energy and the oxidizer species. If we do the same thing for a particle with heterogeneous surface reaction, so let us go to the next page and we can write there. So, if we do the same thing for a particle with heterogeneous surface reaction, we can define B based on coupling between fuel oxidizer species equation. Then what we can define BOF, which we did earlier for oxidizer and energy. Q denotes somewhere like the indication of energy. So, it is energy and oxidizer species. Here we are defining based on the fuel and oxidizer species, and we can define this as BOF, fuel by oxidizer stoichiometry into YO infinity plus YFS divided by 1 minus YFS. This was similar to what we did in the earlier case for evaporation of single droplet. It is almost similar to that, we have defined this, but there is a case when there is no, if there is no volatility, what does that mean? That we can say the mass fraction of the fuel at the surface is going to be equal to 0. So, in that case we can take out this is 0, this is 0. So, eventually the BOF is going to be equal to simply the mixture ratio stoichiometric into the mass fraction of oxidizer at the far field or far from the particle surface, and accordingly one can actually get the consumption rate per unit surface area, one can actually get the consumption rate per unit surface area, and we can get like m dot by 4 pi rp square. So, here I am writing rp is the particle diameter in terms of rho into d by rp ln 1 plus b. So, 1 plus b means now we are saying in terms of oxidizer and fuel species. So, it is becoming 1 plus b means this one. So, it is F by O stoichiometric into y 0 y O infinity. Okay. So, this is mass consumption rate per unit surface area, that we can write it for the particle. Now, having this background, our next task is to find out the combustion time scale, combustion times for the diffusional control combustion regime, and we have to find out the combustion time for the kinetic control combustion regimes, because if you recall we had started our discussion for metal particle combustion regimes for these two cases, one is the diffusional control, another is the kinetic control. So, in our next module I think we can begin this discussion with this time for the diffusional control combustion and kinetic control combustion, and then we will try to understand how the combustion regimes is going to be different for different particles. And of course, our basic understanding on the classification of metal combustion like the heterogeneous combustion and homogeneous combustion, or the gas phase combustion versus the heterogeneous combustion, like we have taken the example of aluminum and boron. So, we will try to understand the burning mechanism of single boron particles and the burning mechanism of aluminum single aluminum particles, because they are the representative of heterogeneous and homogeneous combustion mode. So, I think we can start that discussion in the next module. Till then you please revise this stuff. Okay. Thank you.